All right, so this is going over the second exam. So question number one, freezing acetone is an endothermic process. So first, let's think about what endothermic means, right? Endothermic means that heat is being absorbed by the system. The system is acetone. So if heat was being absorbed by acetone, that would melt acetone, right? Going from a solid to a liquid requires heat. And so this is the opposite of that. This is freezing. So we're going from a liquid to a solid. So that is false. That is an exothermic process. Number two, salts that do not dissolve in water are called soluble. No, that's false. That's exactly what something that's soluble is called. Doesn't necessarily have to be a salt. It could be any solute, right? But if it dissolves in a solvent, could be water, could be something else, it is soluble. Tetrabutyl ammonium chloride is dissolved in a beaker containing dichloromethane. Dichloromethane is the solvent. That is true. That's what it's being dissolved in. That's the definition of solvent. The solute here would be tetrabutyl ammonium chloride. Okay. It takes energy to break the bonds in food molecules. Yes, that's true. Even though you're getting energy out of food, in the long run, you're getting energy by reforming the bonds. So the bonds that you're reforming release more energy than it took to break the bonds, like in sugar, initially, okay? So it takes energy to break all bonds. Whether or not the process overall is exothermic or endothermic depends upon the relative amount of energy gained and lost during the reformation step of the new bonds compared to what energy it took to break the original bonds. Which of the following is true about the kinetic molecular theory? So this theory is basically telling you about ideal gases, okay? Gas particles repel each other, but do not attract each other. No, that's not true. Kinetic molecular theory says that gas particles, i.e. an ideal gas, they don't have any interaction with one another. The volume of a gas particle is considered to be small, about 0.1 milliliters. No, that's not true. This theory in an ideal gas law says that gas particles take up zero volume, okay? The actual individual particles do. The gas as a system aggregate, of course, has volume, PV equals nRT, but the individual particles don't have any volume. Pressure is due to collisions of the gas particles within the wall of the container. That is true. Adding an ideal gas to a closed container will cause a decrease in pressure. No. We know from PV equals nRT that if you add more gas, right, you're pumping up a basketball or something like that, that will increase the pressure, especially if it's a closed container. Question 6. Liquid bromine is added to an aqueous solution of potassium iodide, which reacts to form potassium bromide and solid iodine. For each element, indicate whether the element is oxidized, reduced, or neither oxidized nor reduced during the reaction. So for this one, we're going to have to know our oxidation state rules. All elements in their elemental form are given an oxidation state of 0. So bromine here is going to be 0. And then iodine, I2, is also in its elemental state. So that's going to have an oxidation state of 0. Potassium, remember, potassium is an alkali metal, so that forms +1 ions, and you have a halogen I minus. The halide is going to be a -1, so that tells us the oxidation states there. They're just equal to their ions because they're just simple ions. So potassium is going to be +1, and iodine is going to be -1. And same idea here, bromide is a halide ion, so it's going to be -1, and potassium is staying at +1. So potassium is neither oxidized nor reduced. So it's going to be one of the first two where it says potassium is neither oxidized or reduced. Bromine is oxidized. Let's see. Bromine is going from 0 to -1. And remember, a decrease in oxidation state means it's getting reduced. So that's not true. So it's going to be this one right here, the second one. Bromine is reduced, iodine is oxidized. Yes, goes -1 to 0. Going up, okay, up is oxidized, and potassium just stayed from +1 to -1. Okay, number 7, you fill a balloon with 2.5 moles of gas at 28 degrees C at a pressure of 1.2 atmospheres. What is the volume of the balloon? So this is a static, not changing type of gas problem. Remember, there's 2 types of problems: changing problems and not changing type problems. This is a not changing type of problem. So let me just get some additional whiteboard space here for us. All right, so we are given that the number of moles is 2.50. So that's N in our P equals nRT. Temperature is 28 degrees C, okay? And our pressure is 1.20 atmospheres. So we're not changing, so we're just gonna use P equals nRT. We're not gonna use the 1s and 2s type equation. We're asked for the volume, so we solve for V. That means dividing by P on both sides. That gives you V equals nRT over P. And now we just plug these in, okay? Making sure that our units are good. So moles is what we wanted in. We know the ideal gas constant with the units that was given to us, right? Liters, atmospheres, moles, Kelvin, 0.08206. And the temperature, we have to convert that 28 into 200 into Kelvin. So we add by 273, and that whole thing is going to be divided by the pressure in atmospheres. So if you plug that in to a calculator, you get 51.45 or 51.5 liters. And so that's your final answer there. Okay, so let's go back. Okay, so let's stop this here and we'll keep going on the next problem in the next video.